Hello everyone, we are starting a free open lecture on our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions and get answers online, join our lectures. You can find the link to our Discord in our Telegram channel. To find out the lecture times, join our Telegram channel. Let's calculate the complexity. What can we do? We need to fixate on something consistently now. To apply this method, so we have our heap there, right? Well, first of all, let's just simply reduce it to a single subtree like this, so that we essentially don't have to take into consideration all of them. Because if we basically have D trees, if indeed we calculate exactly the amortized complexity for one tree, then if indeed we do exactly the same thing for D trees, if specifically we want to do it specifically for D trees, then multiply it by D and divide by D, and still we have precisely the same amortized complexity. Now we have one tree. What exactly will interest us here in this context? Suppose this tree has L leaves. Accordingly, this tree has approximately L paths to the root. Essentially, right. Then, if we calculate the complexity on a single path accordingly, to calculate it on all paths from the root to the leaf, we multiply it by L and divide by L, and we kind of get again, essentially, basically, fundamentally, the time is amortized, and now we have finally reached some path of ours, meaning this is our root and this is our leaf. Let's immediately consider the best case, because if there is no star here, and we want to move the key of this one to violate the heap property, we just put a star, and it is obviously from 1. Well, this is an example that we are from 1. That's all okay. We are interested in knowing when we will need to take a lot of steps. Here, let's say, how many steps will we need to take here? The letter M. And here we won't be simplifying anything anymore. Here we will finally start calculating our complexity, amortized. So let's take another look. So first, when we start reducing this key, what do? What will be the complexity of this operation? Well, actually M, because we will take this heap and transform it into what? Well, let's add this here. So this lift went over here, and then I have these things with stars that were there, and I have something else here too. But this is actually not interesting. That is essentially after the first operation, which was executed in M, we essentially transformed our heap into something like bamboo. If we essentially focus on the nodes we were just considering, want to become a cool programmer? Subscribe to our Telegram channel. Now let's try to perform the same operation for these same nodes. What will be its complexity? We already have all the nodes, currently at the root, presently, and then all other operations, no matter how many we do, k in number, k can even be greater than m, as many as we want, we will reduce that many. Here we have a decrease key operation. If it is the root, it will be performed in O one time. So if we want to decrease this key, it will be done in constant time. This one will also be O1 if we want. This one will also be O1 if we want, because they are all at the root and there will be no lifting here. We just update it and we change the heap. This is all done in constant time. So I will perform operations the same way. Like one for each node. At the bottom, well, actually the first one is the heaviest, and for the rest it doesn't really matter. All of them will have a complexity of 1. Then what will be the amortized complexity of such an operation on average? The total number of operations is m plus. Here we have the number of steps, m1, and the complexity of each step is 1. And we made a total of m calls. Then, well, just like in a dynamic array, we reduce and get 1. Also amortized. Hence, decrease key will remove the complexity from 1, but it is amortized. That means some of them will take a long time to execute. Well, just like in a dynamic array, that is, when we perform something for a node, For the first time, it will take quite a long time to compute. In the worst case, we will need to go up, and then it will quickly start for all the nodes we are considering. And then, if we just keep going up here, this one will remain for several paths, because if we calculate for one path, we can say that for other paths, it will be approximately the same. So, I mean, they will definitely not be worse than the worst case scenario. And for a set of trees, they will also not be worse. But we always need to remember that when we perform such decrease key operations, it is important to carefully add additional trees here. Accordingly, if we perform many decrease key operations, the deletion of the minimum will take a bit longer, because, for example, everything was well balanced, and we disrupted the balance with decrease key by not placing it here. Then we will be able to restore the heap, balance it, and it will perform deletions quickly, for example. Well, in conclusion, what I will say is that in reality, despite the fact that 4 out of 5 operations are performed by the unit factory, one of the units, which is amortized, and the removal of the minimum is performed by the amortized algorithm, it will not be significantly more efficient than a regular binary heap, which is probably available in many programming languages in the standard library, implemented either on an array or on a tree. It will not be more efficient than the same binomial heap. Well, again, if we only perform push, stop, and merge, it will indeed be very efficient because the units here are honestly honest. But these honest units can be implemented with just one variable as long as only the minimum needs to be maintained. We will not delete it, nor will we decrease anything. This is somewhat of a theoretical data structure because due to this amortization, it will not significantly outperform a binary heap or a binomial heap if we consider quick operations. But with larger volumes of data, such as those found in big data analytics or large-scale enterprise systems, it will start to show its efficiency and effectiveness in processing and analyzing data compared to these. That is, we need such data sizes where even this unit will be amortized. Much indeed, truly, significantly faster than not, noticeably faster than this logarithm, honestly, for everyone. It's 5 units of time because, again, what is the downside of amortized data structures? Let's say we do something super dumb. For example, we have some queries, and these queries are just a key press. Since indeed, truly, absolutely, really, actually, certainly, undoubtedly, unquestionably, undeniably, verily, genuinely, assuredly, positively, surely, in fact, literally, precisely, exactly, accurately, correctly, rightly, justly, fairly, properly, rightfully, lawfully, legally, legitimately, validly, soundly, well-founded, reasonably, rational, logically, sensibly, wisely, prudently, judiciously, astutely, shrewd. If we consider a large number of queries, each query will be executed in constant time. In reality, let's say if this is user 1, user 2, and user 3, for this one it took 1 unit of time. For this one it took 1 unit. For this one it took 1 unit. But for this one it took n units, meaning they waited much longer than the others. And therefore, if this is somehow critical, then perhaps such a data structure is not suitable. It might be better to use something without amortization. There is, in my humble opinion, a very highly theoretical data structure that allows for the implementation of, well, not exactly a traditional data structure, but rather more thoughts on the Fibonacci heap, specifically on how to effectively remove amortization from here and there so that it works honestly and efficiently throughout the entire rhythm. But it's really intense. Want to become an awesome programmer? Subscribe to our Telegram channel for more tips and tricks and stay updated with the latest programming news.